Hello there, ladies and gentlemen. Welcome back. Today we're going to be talking about exponential and logarithmic models. Basically, we're going to be using equations we've talked about the last couple days and how we can use them to model real-world scenarios and real-world data, okay? So we are going to be, these are the five kind of models that we're mainly going to be focusing on over the next 2 days. Today we're going to basically focus on the first two, exponential growth and decay, which really is kind of one model that's the same thing, ae to the bx and ae to the negative bx, where b has to be greater than 0. Basically, if your b is positive, you have growth. If your b is negative, you have decay. So they're kind of the same model, but just for one growing and one going away, okay? Tomorrow we'll focus on the last three, the Gaussian model, the logistic growth model, and the logarithmic model, okay? But today we're going to mainly focus on the growth and decay exponential model, okay? We're going to kind of basically just see an example of each and what we're going to kind of be asked to do and something to look for when we are looking at these equations. So, for exponential growth, here's an example of an exponential growth problem. The number of households with a digital TV can be predicted in terms of time using the following model. So here, they went ahead and they wrote us an exponential growth model. How do I know that it's growth? I can see this right here is greater than 0. Okay, you can see that portion right there. So I know that this is going to be growing as we go. Okay, t has to be greater than 3 because 3 is representing the year 2003. D is in millions. Okay, so basically we're going from the time 2003, we made time 3 be 2003, and everything greater than that we can represent, and we can show D in millions how many we have. So they want to know, when will the number of households with a digital TV reach 100 million? So what we're going to do is we're going to take our model and we're going to use it to figure out when that's going to happen, okay? So let's say, for example, that you are the government and you have to figure out basically, is it okay, when can we allow companies to switch over from presenting TV in one way versus a digital way? Okay, that actually was something that happened in the mid-2000s, where eventually certain kinds of television outlets that were going out, they don't allow anymore. You have to have a digital TV, and they waited till they knew enough people had digital TVs to make that switch. So if the number was, when 100 million people have them, that's when we're willing to do that. Well, let's figure out when that's going to be so we make sure we're ready for that. So we're going to go ahead, we'll put 100 in for D, because remember it's in millions, so 100 million would be represented by 100. That's going to equal 30.92 E to the 0.1171 T, okay? Well, I'm now going to go ahead and solve this equation for T, and the way I'm going to do that is how I solve an exponential. I'm going to divide by 30.92, then take the natural log of both sides, and then divide by 0.1171, okay? So we'll start by dividing by 30.92. I have my calculator with me. So we'll do 100 divided by 30.92, and I got 3.23415. I'm going to include a bunch of decimal places. The more decimal places I include, the less rounding error I will have. So feel free to include as many as you want. We're then going to go ahead and to get rid of this E, we'll take the natural log of each side. That's going to make this cancel out. I'm going to get the natural log of 3.23415 equals 0.1171t. And then I'm going to divide by the 0.1171 on each side. So I'm going to get the natural log of 3.23415 over 0.1171 is going to equal t. Okay? That's the exact answer. Obviously, that's not a very good answer. Like, what year is that? I don't know. Okay? So we need to actually type in and get the approximate answer so we can give a good idea about when that's going to be. So the natural log of 3.23415 divided by 0.1171 is going to be a little over 10. I got 10.02, and that's years for time. Okay, so in about It's not in 10 years, but remember, it's from the year 2003, so 10 is around the year 2010. So around 2010, 100 million people will have a digital TV. We can go ahead and we can maybe switch the signals or whatever. All right, so there's an example of an exponential growth model and how we can use it to make a prediction or make a decision on something that we're doing, okay? How about exponential decay? So again, this is basically the same sort of model, except in this instance, the B value, that value up there is going to be negative as opposed to positive, and that's what's going to make it decay as we go along, okay? So, and if you want to look at one thing that might be helpful is on page 423 in your textbook, you're going to see not only these equations, the generic versions of each model, but you'll also see a graph to kind of give you an idea about what each one looks like, okay? Exponential growth obviously is an exponential going up, decay is an exponential going down, and decaying as we go. So, one example of exponential decay is actually by what's called the half-life of something and doing a method called carbon dating, all right? So scientists can determine the age of an artifact by looking at how much carbon has decayed from the item. This is known as carbon dating. The model to determine the age of an artifact is 1 over 10 to the 12th e to the negative t blah, 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 equals r, where t is time in years, and r is what's the ratio of carbon-14 to carbon-12. If a newly discovered fossil has a carbon ratio of 1 over 10 to the 13th, how old is the fossil, okay? So we want to figure out, using this equation, how old the fossil is if r is equal to this. So again, very similar to what we did on the other one. We're going to have 1 over 10 to the 12th e to the negative t over 8223 equals 1 over 10 to the 13th, because we're going to fill that in for r. That's the ratio of carbon-14 that is left, okay? So we're then going to go ahead and multiply both sides by 10 to the 12th. I'm going to get e to the negative t over 8,223 equals, and 10 to the 12th times 1 over 10 to the 13th is going to be 1 to the 10th. I'll take the natural log of both sides. So negative t divided by 8,223 equals the natural log of 1/10. And then I'm going to multiply both sides by negative 8,223. And that's going to be my answer. So let's put that in our calculator. We have negative 8,223 times the natural log of 1 over 10. And I got 18,934.16. Okay, so in terms of the age of the artifact, how long has this been around? It looks like this artifact's been around 18,000 years. That's a pretty large number, okay? So that would be the age of this artifact based off of the data we have here, okay? All right, so that's an example of exponential decay. Those are the main two models. Those are the two models we'll be dealing with today, and tomorrow we'll talk about a couple more, all right? Thank you all for watching.